Alright, intermediate trig, let's do this. So, when you're talking about trigonometry for beginners, you're almost exclusively talking about the right triangle. However, mathematicians of old have figured out how to conquer lands beyond for these functions. For one, you can express trig functions through a right triangle on the unit circle, which allows any angle to be expressed as an input to a trig function. For another, there exist infinite sums for each trig function. These are rather complicated, and generally in math we want an exact value rather than a close approximation. This, however, is how computers compute trigonometric values. The one we're interested right now is a method for computing a trig function for the angles on any triangle. If we want to express the sine of this angle A as a ratio, we can use an altitude, also known as the height, the line that is perpendicular to this line and intersecting this point. Since these two lines are perpendicular, this boy right here is a right angle, and this boy here is a right triangle. Now we can just use the original definition of sine to find that the sine of angle A is the length of the altitude divided by the length of this side. I'll admit that this method is kind of cheating. How do you find the sine of an angle on a non-right triangle? Easy, just make it a right triangle. This method also shifts the problem from the angle itself to the altitude, which still requires trigonometric functions to calculate. Despite these problems, however, this method will be very useful for when we talk about the law of sines and the law of cosines. The law of sines states that the ratio between the sine of an angle and its opposite side is the same between all three angles of a given triangle. Let's take this random triangle here. If we divide the sines of all three angles by the lengths of their corresponding opposite sides, or divide the opposite sides by the sines, it doesn't actually matter, then we get the same value for all three. Pretty cool, right? But where in the world did we get that law from? Well, if we have just these two angles here and draw the altitude, we can find the sine for both of them. Sine is opposite over hypotenuse, so we get the sine value for these two like so. We can then solve for the length of the altitude by multiplying by the length of A for this one and the length of B for this one. We now have two different expressions that are both equal to x. By setting them equal to each other and then rewriting, we can see that we get the same ratio from the law of sines, showing how sine of A over capital A equals sine of B over capital B. If we drew a different altitude,
we could show how sine of A over capital A equals sine of C over capital C, or how sine B over capital B equals sine C over capital C.
Now, as great as this is, there are still a couple edge cases that we need to look at. When you have two sines and a non-included angle, which is an angle that isn't between the two sides, it means that you've just stumbled across the ambiguous case. If we're given a triangle with side lengths 10 and 6 with a non-included angle of 33 degrees and asked to solve for beta, we can do the same thing as before and get a value of about 65 degrees. All is well in the world until my man Gauss knocks on the door and loudly exclaims, "There exists a second solution!" He jots down a different triangle. It still has the same two sides and given angle you had, but a different value of beta at around 115 degrees. You examine his illustration, and the solution works. You thank Gauss for his findings and wish him a happy birthday. As you can see, there are two different triangles which have our specified sides and angle. This ambiguity comes from the arcsine function. You see, because the arcsine function is a function, it can only return one value. But if we look at the unit circle, we can see that basically every sine value can be achieved from two different angles. We can get the corresponding angle by subtracting the original angle from 180 degrees. In our example, 115 degrees is in fact 180 degrees minus 65 degrees. When dealing with the ambiguous case, it's important to remember that not every triangle will have multiple solutions. Here's a simple test to determine whether a given solution works. If you can add your solution and the given angle together and get a value of less than 180 degrees, then that solution will work. Otherwise, the solution can't work because the angles of a triangle cannot be greater than 180 degrees. This means you can have one solution, two solutions, or no solutions, although that last one isn't really because of the ambiguous case. Actually, let's talk no solutions. No solutions isn't just the ambiguous case or the law of sines. It's actually just because the equation, the actual triangle, is impossible. Like, we'll have to take the arcsine of a number with a value greater than 1. This is impossible, since the sine function can only yield values between 1 and -1. Well, until we start using our imagination, but that's a video for another time. Alright, so now it's time to talk about the law of cosines, which is kinda like the law of sines' annoying little brother. But, we have to love each trigonometric function equally, so without further ado, the boy. Yeah, kinda painful, kinda difficult to put into words, but we can derive the formula nonetheless. Let's get out our triangle once again. Let's name the segments created by the altitude x and y. We already saw how our altitude can be found with this expression. Similarly, this segment x can be found with this expression, and the value of y with this expression. Now, for this right triangle, we're going to pull out the Pythagorean Theorem. So we plug these two values in and simplify. Let's expand these two squares here. For the first one, a and the sine of c are multiplied, so we expand like so. For here, b and negative a cosine c are being added, so we simplify like so. Now we rearrange some terms and, hey, wait a minute, we have an a squared we can factor out here. And now we have sine squared plus cosine squared. And if you remember from one of the Pythagorean identities, this simplifies to 1. Now we simplify a bit more and, yep, that's the law of cosines. Not very beautiful compared to the law of sines, but hey, it's still useful, you know? At this point, if you're like me, you might wonder if there's some law of tangents, or reciprocal functions, or inverse functions. And the answer is, yes? I mean, covering these laws is beyond the scope of this video, and frankly, the scope of my knowledge, so not going to. Now, the law of sines has a pretty cool property that I haven't mentioned yet. In fact, it's pretty important. Not for, like, solving problems with the law of sines, but, like, the underlying heart of the law of sines. These ratios are written like this for a reason. As in, you could take the reciprocal of this and it would be the same, maybe even a bit neater.
I don't like dividing by the frickin' sine, alright?
We write it like this because each of these ratios is exactly equal to the diameter of the circle that circumscribes the triangle. In fact, we could frame our law of sines proof around this circle to not only prove the law of sines, but also show that each of these ratios is equal to this diameter. So if it's keeping you up at night why it's written length over sine rather than sine over length, just remember that it's because of this circumscribey circle boy, and its diameter. Well, that's it for this video, and that means it's time for another fun fact. Did you know that there are more people in the world who fluently speak Klingon than people who can fluently speak Cherokee? But guys, can we smash that like button? Can we get 2 likes on this video? And as always, thanks for watching.